is the Pythagorean theorem wrong? Think about the 3, 4, 5 triangle. The 3, 4, 5 triangle, the hypotenuse at length 5 is obviously less distance than going along both legs of the triangle, which are 3 and 4, that add up to 7. Now consider this stuff. Think of a person walking along a city grid. They could walk 3 blocks one direction, and then 4 blocks another direction to make a total of 7 blocks. Or they could do the raster-like way, which would be to go up one, then side one, up one, then side one, up one, then side one. If you graph it, going up one, then side one, the entire distance, actually causes the length of the longer leg times 2 distance units, or 8 distance units. So actually, it's 8 distance units, which is a greater length than the 7 of just going one of the legs than the other. So that's a situation where the graininess, or the raster effect, causes the hypotenuse to actually be a longer length than both of the legs combined. Now, let's have a look at another place where the Pythagorean theorem is actually different than a descriptor of the shortest length between 2 points. Non-Euclidean geometry is well known. If you place a triangle on the surface of a sphere, you can find many occasions where a straight line is different than the shortest length between 2 points. That's well known. Now, thinking again about a raster effect, what happens if you use a different shape? What if you were to use circles? So imagine visualize somebody's creating a situation made of circles. And remember, things like atoms have mathematical approximations which are somewhat similar to spheres. So sometimes when people make equations to describe the behavior of atoms, they'll use trigonometry, or they'll draw circles. So visualize a triangle, and it's made of 3 circles in a row at the base, and then 4 circles up high. And there it is, it's all made of circles. And if you actually were to travel the perimeter of this thing, which is like a triangle, but it's actually an arrangement of circles, the pi diameter is the entire circumference of each circle, and you only have to sort of go hippity-hop, hippity-hop, hippity-hop each half diameter, then what you get is you get a situation where they are the Pythagorean theorem is functional again. So we can see that it depends on the shape of the repeated unit, what the actual rightness of the trigonometric ratios are. Now there's another version where it's arbitrary. Visualize or think of a fractal. Now a fractal at a particular line drawn through it could have a non-finite surface area. So even though a person could very handily draw a 3, 4, 5 triangle on, say, what looked like a computer printout of a fractal, they could have one side that was of non-finite length and 2 sides that were of finite length. Or they could have the legs of the triangle be of non-finite length and the hypotenuse be finite length. So we can actually see that many things that look like a triangle completely violate or completely are different than the Pythagorean theorem. Now here's why this could matter. Think of the quantum absorption of a photon and then its re-emission at an atom. Now, that atom could be obeying the Pythagorean theorem, which is the basis of many trigonometric ratios. So when you see physics and they're using things like COS or arc COS or tangent or any of those things, then it's possible that for certain actual measurable systems, those equations are they lack adequacy to describe the functional anisotropy of the system. Now, I could say rasterization because there's that's one way to look at it, but rasterization implies a square or a cubic form, whereas you can say anisotropy and then you actually create a situation where there's a wide variety of possible actual physical bases to the things that people had been describing with trigonometry. So, are there entire physical systems which should be described with mathematics different than trigonometry because trigonometry depends on the anisotropy of the system? Well, one possibility is that quantum levels, as they're called, depend on the anisotropy of the system. That's because I think you'd get a functional Pythagorean theorem if absorption and re-emission were one-dimensional. But I think that scientists have proven that at least some of the time when an atom absorbs a photon and then re-emits it, it re-emits it at a direction different than the direction of absorption, which means that quantum levels, because they're all steppy, could have rasterization, and rasterization means that the Pythagorean theorem lacks accuracy describing the distance that an energy packet would have to take to be emitted. So we see that with rasterization, which goes quite along with quantum levels, that the actual distance, the energy distance, or the physical distance, of a re-emitted photon could vary widely according to Powell. It's possible that there's a new mathematics which completely is different than trigonometry, which would cause quantum levels to be more explainable as well as more predictable. So it could be a alternative or replacement to quantum theory to mathematically account or mathematically describe something different than the rasterization present at quantum levels. It could be based on actual observations of the direction of photon absorption compared with possible things like differences between phosphorescence delays or fluorescence delays or lasing delays at the actual direction of the re-emitted photon.